Okay, let's do problem 9.35 of Sontag because it's a slightly subtle concept involved in this problem. So the diagram is as follows. There's a heat exchanger into which there is one inlet and one exit. Okay, so the fluid that goes in is R22, and this is heated by a heat pump. So it is heated by a heat pump. So a heat pump absorbs heat from a lower temperature. It requires some work and it is giving an amount of heat. Rate of heat transfer is QH to the R22. So the R22 is 2 kg per second. The inlet state is 500 kPa and saturated vapor and 500, and it is heated at constant pressure to 60 degrees Celsius. So this exit state is 500 kPa and 60 degrees Celsius. What is the heat supplied by the pump? The heat supplied by the pump is simply the difference in the enthalpies. That's very easy. The ambient is 300 Kelvin. Okay, we have to assume that everything is reversible and correspondingly find the work input. Okay, so first things first, control volume as the heat exchanger. So for a steady state, steady flow process with only one input and one output, 0 equal to Q dot plus M dot HI minus HE minus W dot. W dot is equal to 0. So Q dot equal to M dot HE minus HI. M dot is 2 kg per second, and exit states are known and the inlet states are known. Okay, so this is problem 9.35. HE equal to enthalpy of R22 at T equal to 60 and P equal to 500 kilopascal. HI equal to enthalpy of R22 at X equal to 1 and P equal to 500. So Q dot equal to M dot multiplied by HE minus HI. M dot is equal to 2. Okay, let's see what the Q dot is obtained. Q dot is 86.7. so this is the heat absorbed by the system. So obviously, okay, so this is the heat absorbed by the system. Now what? So how do I find out the work? Okay, I know what QH is. I cannot relate QH to TH because the TH is varying. Even if I assume that everything is reversible, this thing is not a Carnot cycle because the TH is varying. If the TH was fixed, then I can simply relate QH and TH and QL and TL and then find out the work done. Okay. However, if TH is varying, I do not know how that. So to know what how the TH is varying, let us quickly see what the inlet temperature is. Okay, the inlet temperature will be at this particular condition. Okay, so that is equal to what? This. So the T inlet is at 0.1148 degrees Celsius. So this is at 0.1148 degrees Celsius and it is going to 60 degrees Celsius. So TH is continuously varying. So to avoid this problem, what we can do is we can make a control volume which consists of the entire thing, okay, and then try to find out what is going on. See, the idea is very simple. You must find out what the rate of work done is, okay. So we must somehow make use of the first laws and second laws for the entire control volume. If this is the entire control volume, there is one mass inlet, one mass outlet, one work done and one heat transfer, okay. So for the entire control mass, if I write down the first law, for a steady state steady flow process, this is 0 equal to Q dot L, because heat is absorbed by the system, plus M dot HI minus M dot HE minus W. This is W dot. If I write down the second law, 0 equal to Q dot L by TL plus M dot SI minus M dot SE plus S gen dot. But if I assume the process is reversible, then S gen dot is equal to 0. Thus I can relate QL and S dot I and S dot E. See, the whole business of QH has vanished, because whatever QH was absorbed by this is rejected by this. So QH is only an internal heat transfer between the heat exchanger and the heat pump. Because we have taken the control volume inclusive of this heat pump and the heat exchanger, this QH has vanished from our calculation. So Q dot L is equal to TL multiplied by M dot SE minus SI. Okay, let's see. So this is Q dot H. Q dot L is equal to M dot times TL multiplied by SE minus SI, where TL is equal to 300 Kelvin and SI equal to entropy of R22 at X equal to 1, P equal to 500, which is the inlet state, and SE entropy of R22 at T equal to 60 and P equal to 500. Okay, let's see. So the QL is equal to 86.03. So heat is absorbed by the system. Okay. Correspondingly, all that is remaining to do is find out the work done. So from this particular equation, the expression for work done, the power input is equal to Q dot L plus M dot multiplied by HI minus HE. Okay. So the work input required is minus 0.6644. Okay. This is the work done on the system. So this work done should obviously be equal to QH minus QL but I leave that up to you to think. Okay. But this is how you perform the calculation.